So today we're going to have a little bit of fun trying to demystify quantum spin. Okay, what I'm going to do is I'm going to show you some software I wrote to do the belt trick, and we're going to do all kinds of other fun stuff. But the purpose of this video is to demystify quantum spin using the 4x4 matrix version of Quaternions that I have been working with for quite some time now. And so what we're going to need to do is we're going to need to do a quick review of the demystifying complex numbers, which leads to demystifying Quaternions, which will lead to the demystification, I hope, of the of quantum spin. So in the demystification of complex numbers, we found that the square root, both the square root of +1 and the square root of -1 has two solutions. The square root of +1 has two solutions, 1 and -1, and the square root of -1 has two solutions, which is +I and -I. And under the hood, +1 and -1 are these 2x2 matrices. So +1 is this 2x2 matrix with positive ones on the forward diagonal, and -1 is this 2x2 matrix with -1 on the forward diagonal. And so in a similar manner, +I is this 2x2 matrix with 1 and -1 on the backward diagonal, and -I is -1 and +1 on the backward diagonal. And so when you implement the square root of 1 and square root of -1 in 2x2 matrix form, you end up with these four matrices. And these four matrices form a group. In group theory, these four matrices form a closed group. And what that means is that any sort of operation that you do using these matrices, so if I square this matrix, I get this matrix, and if I square this matrix, I get this matrix, and if I square this matrix, I get this matrix, and if I square this matrix, I also get this matrix. And if I multiply this matrix by this matrix, I get this matrix. And so whatever operation you do using only these matrices, you're going to end up with one of the matrices in the group. So when you want to use these matrices to do rotations, what we need to do is map this out in a little bit more detail. So I'm going to quickly review this, but you can pause the slide and have a look at it in more detail. But really, I'm just dealing with the square root of -1, because the square root of +1 is pretty straightforward. But the square root of -1 is what people find kind of difficult to understand. And so here we have the square root of -1 is I, +I and -I, and +I and -I are this matrix under the hood, and this matrix is actually this matrix in disguise. And so this is Euler's formula in disguise. So this is cos theta plus I sine theta. And in this case, in the +I and -I, the theta is equal to 90 degrees. So I and -I are 90-degree rotations, and these two matrices are correspond to rotation matrices. Okay, so I, +I and -I correspond to 90-degree rotations. Now we can generalize that using Euler's formula. So here is Euler's formula, which is e to the square root of -1 theta, which is e to the I theta, or e to the -I theta. And e to the I theta is this formula here, cos theta plus I sine theta. And e to the -I theta is this formula here, cos of theta minus I sine theta. And under the hood, these two formulas are actually this matrix, these two matrices here, with cos theta on the forward diagonal and sine theta on the minus diagonal. And the forward diagonal has the same sense. and the backward diagonal, the two entries in the backward diagonal have opposite sense. Okay, so e to the I theta is this matrix here, and e to the minus I theta is this matrix right here. So next we're going to do a quick review of demystifying quaternions. Okay, so I'm just going to start with the four matrices, the four quaternion matrices, the 4x4 matrices. So under the hood, quaternions are 4x4 matrices. And so the identity matrix and the 4x4 identity matrix looks like this. So this would be considered, I use this notation when I put square brackets around a value. It means that this is a 4x4 matrix, okay, or it's a matrix in general, but in this case of quaternions, it's a 4x4 matrix. And so the quaternion, the scalar quaternion identity, the identity matrix has ones on the forward diagonal. And so the quaternion, and so this basically, when you multiply a value, a vector, a point, a coordinate, a location, however you want to interpret it, by this matrix, it leaves the matrix unchanged. So then we've got the I matrix. So the positive I matrix is equal to this matrix here. So you've got +1, -1, -1, +1 in these locations and 0 everywhere else. Okay, and so this is the I matrix, and this corresponds to a rotation about x, the x-axis, in the yz plane. So if you use this matrix directly, it would correspond to a rotation about x in the yz plane. Okay, so then we've got J, so this is why I call this QX. So this is QX is a rotation about the x-axis, and then QY is a rotation about the y-axis. So J corresponds to a 90-degree rotation about the y-axis, and it's it's got ones in these locations. Okay, so +1, +1, -1, -1, and this corresponds to a rotation about the y-axis in the zx plane. Okay, and then we've got the K matrix, which has ones in these locations. So you've got +1, -1, +1, -1, and this course, I call it QZ because this corresponds to a rotation about the z-axis in the xy plane. So here is the generalized version of the quaternion matrix. Q is equal to WR plus XI plus YJ plus ZK. And when you write this under the hood, this formula here is this matrix here, where you have W's on the forward diagonal, okay, and you have X's in these locations. So W corresponds to the scalar, which is basically this matrix here. Okay, so when you take W and multiply it by the identity matrix, then W will appear in these locations here. And then when you take I and multiply it by the I matrix, then when you take X and multiply it by the I matrix, then X appears in these locations here. And they have the same sense as the matrix here, as the identity. This is the I matrix with plus, minus, plus, minus, plus, and the X's appear in those locations plus, minus, minus, plus. Okay, and then similarly Y, when you multiply Y by the J matrix, then Y appears in these locations here. And when you multiply Z by the K matrix, okay, the K matrix here, then Z will appear in locations of the K matrix. Okay, so this is the generalized quaternion matrix, which basically under the hood, the identities, what we call it, the units of the quaternion matrix, when you multiply the W, X, Y, Z by the identities, by the units of the quaternion matrix, then you end up with this matrix here. Okay, so Euler's formula in quaternion form looks like this. So cos of theta plus I sine theta plus j sine theta plus k sine theta looks like this under the hood. So in 4x4 matrix form, Euler's formula, Quaternion formula looks like this here, okay? And then there's one more step we have to take, which we've done before. So we've done all this before. This is just a quick review. In order to use these matrices to do the spins for the quantum spins, okay, we need to add the axis. So we need to multiply each of these terms by the amount of the axis that we're rotating about. And so with quaternions, we're able to rotate about an arbitrary axis, and the fraction of that axis needs to be multiplied by the sine and cos terms. And and we need to apply the angle divided by 2 because we need to do 2 operations in order to do a quaternion rotation. We need to do it in 2 parts. So we need to use the quaternion and the complex conjugate. So the complex conjugate of this matrix here is where if you flip this matrix about the 4 diagonals, or you basically negate all the sign terms, then you're going to get the complex conjugate. And so when you want to take a quaternion point or quaternion vector, if you want to use that terminology, if you want to rotate that location about an arbitrary axis, you need to take the quaternion, you need to take the point and multiply it by the quaternion, right? And then you need to take the output of that and multiply it by the complex conjugate, by this matrix here. And so I'm going to show you the code for all of this. I just wanted to do a quick review. If you want to go into more detail, then watch my videos that have the word demystifying in it. So demystifying complex numbers, demystifying quaternions. I have another video called demystifying Hamilton's quaternions, which gets into more detail about how the quaternion matrix can be extracted from Hamilton's paper. So if you want to go back and review that before we move forward onto this, then I encourage you to do that. So in order to demystify quantum spin, what we're going to need to do is we're going to need to talk about, what is quantum spin. So we need to know what quantum spin is before we can demystify it. So what I've done is I'm going to use ChatGPT. Okay, so I use ChatGPT because it words things very nicely. I find that it words things very nicely. I know a lot of people kind of give me a hard time, or sometimes they belittle me a little bit for using ChatGPT, but I use ChatGPT a lot to help me demystify quantum spin. And so I'm going to show you sort of the thought process I went through to demystify quantum spin. Okay, so I asked ChatGPT, what is quantum spin? Quantum spin is an intrinsic form of angular momentum carried by elementary particles such as electrons, protons, and neutrons. Unlike classical spinning objects, quantum spin doesn't represent literal spinning in space, but it is a fundamental property of particles that dictate their behavior in quantum fields. Now, this is the standard definition of quantum spin. Okay, I don't necessarily agree with everything that is being said right now, but this is what is being taught in school, and this is what was taught to me, and so I'm going to try and demystify all of this gobbledygook too. Okay, so here are some key aspects of quantum spin. So there's a quantized property. So spin is quantized, meaning it can only take on certain discrete values. For electrons, it is typically described as spin up or spin down. Intrinsic angular momentum. So spin is a type of angular momentum that doesn't arise from actual motion through space, as a particle, a thing that you would throw across the room as a motion in space. Okay, so it's not an actual motion through space, but an intrinsic characteristic of particles. I don't necessarily agree with the statement, but this is what is being taught in terms of quantum spin. So spin and magnetic moment. So particles with spin often exhibit magnetic moments, meaning they interact with magnetic fields. This property is critical for phenomena such as electron behavior in atoms, where electron spin affects energy levels, and also in nuclear magnetic resonance, which I have a little bit of experience with in the field of medical imaging. So spin states. Okay, so this is where it's interesting because I had a conversation with ChatGPT earlier about quantum spins, and so it says quantum spins, and it put the word orientation in here. Okay, so it said quantum spin states, which you prefer to call orientations. Me, I asked ChatGPT whether quantum states are really just orientations, and it agreed with me that quantum spin is really just quantum states are orientations. Okay, so this is was a huge breakthrough for me mentally, because when you think of states, I had a hard time visualizing states. And so I didn't know what a quantum state was. I wasn't sure what a quantum state was. And through my research, I realized that quantum spin states are really just orientations. And so I can visualize an orientation. I know what that is. I know what that looks like. And so quantum spin states, which I prefer to refer to as orientations, are described in quantum mechanics using mathematical objects called the spinor. Spinor, spin-or, I'm not sure how to pronounce that properly, but I'm going to call it a spinor or a spinor. I'll call it whatever I feel like at the time. Okay, so these spinors define how the particles spin. The particles' spin orientation changes under rotations. Okay, so we're talking about we're talking about orientations here. When we talk about quantum spin, we're talking about the changing of the orientation. And I think that's a really important piece of the puzzle that I wasn't clear on until I started doing this research. Okay, so applications. So spin is important in various fields such as quantum computing, blah, 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 blah. Okay, so in simple terms, quantum spin is a key characteristic of particles that has no classical counterpart, but plays a critical role in the structure of interactions of matter and at the quantum level. Now, this kind of confuses me because I convinced ChatGPT to admit that spin states are orientation, and orientations, there is a classical analogy to orientations in standard mechanics, and not quantum mechanics, but in normal mechanics. And so I found I find this whole, quantum is different than classical mechanics to be a little maybe disingenuous, because orientation is something that we can perceive in the mechanical sense. And so I'm just going to show you let's see if I can find my animation here. Okay, so here's an animation I did that shows this is actually the belt trick. This is quantum mechanics. What I'm showing you here is the basis of quantum mechanics, which I was able to implement using the 4x4 matrix version of Quaternions. I didn't have to use the Pauli Matrices. We're going to talk about Pauli Matrices in a second, but I didn't need to use Pauli Matrices to do a simulation of the basis of quantum mechanics, which is the belt trick. So the next question I asked ChatGPT was, couldn't quantum spin be better thought of as precession? Okay, so here we see precession going on. Couldn't quantum spin be better thought of as precession? So yes, thinking of quantum spin as a form of precession is actually a helpful analogy, especially when considering how particles' spin interact with external fields. In classical mechanics, precession refers to the wobbling motion of a spinning object like a gyroscope in response to external forces such as gravity or magnetic fields. While quantum spin itself doesn't imply literal rotation or classical spinning, the analogy of precession is relevant in the context of how the spin behaves as in an external magnetic field. So this phenomenon is known as Larmor precession. Now, people that are familiar with Ken Wheeler's language, you know that he talks about Larmor precession quite a bit. And so it describes the way particles spin or wobble around a direction of an external magnetic field. Okay? So when a particle with spin is placed in a magnetic field, the magnetic moment related to the particle spin interacts with the field, causing the spin to precess. Okay, causing the spin to precess around a magnetic field axis. Okay, so this would be a magnetic field axis that it's spinning around, which we refer to as the Larmor frequency. So it's the frequency of precession. So this is similar to how a spinning top precesses under the influence of gravity. So there is a classical analogy to quantum spin, which is precession. Okay, so quantum precession in quantum mechanics, the spin up and spin down orientations can be thought of as special cases of how a particle spin vector aligns relative to an external field. The superposition of these spin states, these orientations, results in a dynamic process where the overall spin direction evolves in time, right? Evolves in time, similar to classical precession. Okay, so I'm not going to talk about this anymore. So I am going to think of quantum spin as precession, and in the software that I developed with the help of ChatGPT and Chantal Roth, because the software originally came from Chantal Roth, and I got the software from her. She converted. Her software is written in Unity. She got ChatGPT to convert her code from Unity to JavaScript, and then I got ChatGPT to convert from JavaScript to the P5JS platform, which is based on JavaScript. And so ChatGPT was very, very, very helpful in the process of me generating my software and me being able to explain this to you using my software. So next we're going to talk about the Pauli matrices. Okay, so I asked ChatGPT, what role do Pauli matrices play in the definition of quantum spin? Pauli matrices play a fundamental role in the mathematical description of quantum spin, especially for spin 1/2 particles like electrons. They provide a compact way to express spin operators and are essential in the formulation of quantum mechanics, particularly in the representation of spin states and their transformations. Okay, so the key role of Pauli matrices are as follows. Okay, they are spin operators. They're called spin operators. Quantum spin for spin 1/2 particles like electron is described by spin operators, and they correspond to the 3 spatial directions x, y, and z. These operators are represented by Pauli matrices. Okay, so these are the 3 Pauli matrices. They are 2x2 matrices, but each element in this matrix is actually a complex number. And that's important, and that's why it was important for me to review complex numbers, because basically each entry into this matrix is itself a 2x2 matrix. Okay, so sigma x is this matrix, sigma y is this matrix, sigma z is this matrix. These matrices act on spinors, they act on quantum states, orientations. So these spinors act on orientations and correspond to measurements of spin projection along the x, y, and z axis. And so I'm not going to get into any more details about this. What I want to do is I want to show you how I convert, and this is information I also got from ChatGPT. I want to show you how to convert from the Pauli matrices to the 4x4 matrix version of Quaternions, and which are rotation matrices, and I want to show you how to use the 4x4 matrix version of Quaternions to do this. Okay, so this is an implementation of what could basically be thought of as quantum spin. This is the belt trick that you may have heard about, and so we are going to use the 4x4 matrices Quaternion matrices to generate these animations, and hopefully through this process we will demystify quantum spin. So here are the three Pauli matrices that I showed you in the previous slide. Okay, so this is referred to as sigma x. Okay, this is the Pauli matrice, and this Pauli matrix is associated with the x-axis. Okay, and then we got sigma y and sigma z. So sigma x, sigma y, and sigma z are associated with the x-axis, the y-axis, and the z-axis. So what I said earlier, what I told you earlier, was that each of these entries in the 2x2 matrix, Pauli matrix, is itself a complex number, and so it is itself a 2x2 matrix. So each entry in these 2x2 matrices are in fact themselves 2x2 matrices, and so you can take each entry in these matrices and build a 4x4 matrix. Okay, so this 0 here corresponds to this quadrant of the 4x4 matrix. Okay, and so and this 1 here corresponds to this quadrant, and this 1 here corresponds to this quadrant, and this element here corresponds to this quadrant. Okay, so in this quadrant here I put in zeros, in this quadrant here I put in zeros, in this quadrant here I put in the identity matrix because this is the complex number 1. Okay, let's go back to my complex matrices. Okay, so the positive 1 is actually the identity matrix. Okay, so the identity matrix goes here, and the identity matrix goes here. So this is the complex value of 1, and this is the complex value of 1. Okay, and so here in this matrix here, we've got minus I and positive I in these positions here. In the 2x2 matrix, of course, wherever you have 0, you just put zeros into the 4 entries. But here we have minus I, and as you will see from this slide here, minus I is minus 1 and plus 1, right? So we put minus 1 and plus 1 and zeros into this quadrant. So we put the imaginary, the 2x2 matrix version of minus I into this quadrant, and we put the 2x2 matrix version of positive I into this quadrant. Okay, and so then we have sigma z, where we put the identity matrix into this quadrant, and we put the negative identity matrix into this quadrant. So this is how we can convert from the 2x2 matrix form with where each entry is a complex value and convert that to a 4x4 matrix like we did with the Quaternions, so that each entry in the matrix is a real value, is a real imponderable number. So converting from Pauli matrices to the Quaternion 4x4 matrices actually turns out to be quite simple. And so we're just going to do it one at a time. We're going to take the sigma x, and we're going to, what we do is we take each of these matrices and we multiply it by I. Okay, we multiply it by the 2x2 matrix version of I. Okay, so it's easier to see if you look at it this way. So if you take I and multiply it by sigma x, basically you're taking I and multiplying it by the 2x2 matrix where each entry is complex. So in a way, I is being treated like a scalar here. So when you multiply I by the complex 2x2 matrix, then you end up with I times 0 is 0, I times 1 is 1, I times 1 is I, and I times 0 is 0. So you end up with this matrix. And so when you convert this matrix to the 4x4 matrix form, so as you know, the I in 2x2 matrix, so you put zeros in this quadrant, you put zeros in this quadrant, you put I in this quadrant, and you put I in this quadrant. And so you end up with the K matrix from the Quaternion matrix. Okay, so you end up with this matrix here. Okay, so I times sigma x is actually equal to the K matrix. Okay, and we'll talk about this in a sec, because this is basically when you multiply the Pauli matrices by I, you're going to be 90 degrees out of phase with the Pauli matrices. So the Pauli matrices are 90 degrees out of phase with the Quaternions. So here we've got sigma y. If you multiply I by sigma y, then you end up with, so I times minus I. Well, let's do I times I. So I times I is equal to -1. We know that. I times minus I therefore equals to +1. And so when you convert this to the 4x4 matrix of Quaternions, you end up with the J matrix from the 4x4 matrix version of Quaternions. So you end up with this matrix right here. Okay, so then we'll do the next one. So we'll do I times sigma z. So I times 1 is I times -1 is minus I. When you expand this to the 4x4 matrix form, you end up with +1 -1 -1 +1. And this is actually the I matrix. It's the I matrix from my set of Quaternion matrices. Okay, so we're going to put these all on one page, and you'll see that I times sigma x gives us Quaternion z. It gives us K. It gives us the K matrix in Quaternions. And I times sigma y gives us the J matrix, and I times sigma z gives us the I matrix, which is QX. So you've got Z, Y, X. So you got X, Y, Z converts to Z, Y, X. So the Y doesn't change, but X and Z change places. And so the Pauli matrices, it looks to me, are 90 degrees sort of out of phase. X becomes Z, Z becomes X. And it's a rotation. For X rotates to Z and Z rotates to X. And that's what this multiplying by I does. If it didn't do that, I'd be very surprised. Okay, so that is the difference between the Pauli matrices and the Quaternions, is that they correspond to, the axes are a little bit different, but doesn't really matter. I am now able to use, now that I know how to convert from Pauli matrices to Quaternions, I know that I can use the Quaternions to do everything that the Pauli matrices do. So in the next video, I'm going to actually leave this video at this point and to give you a chance to ponder what I just said. But in the next video, what I'm going to do is I'm going to show you how I use the 4x4 matrices to implement the belt trick. And I'm also going to show you how I am going to use this approach to develop the medium, the medium for the propagation of light, which is also the medium for the propagation of the particle waves that John Mackin talks about in his research, and the ohm particle, which I talk about in my research, which are one and the same thing. So John Mackin's standing wave is my ohm particle wave. That is a scalable, fractally scalable construct. So in the next video, I will show you how I implemented this code. Okay, there's some really cool things that this software can do. Okay, I'm not going to get into those details right now because I want to take more time to show you the code. And this video is getting quite long, so I don't want my videos to be too long, because I know people are going to, maybe not watch them if the video is too long. So in the next video, which maybe I'll release later on today or maybe in the next couple of days, I will show you how this software works. Okay, and I will then give you the code. So this is all written in P5.js. I will give you the code, and you can play around with it yourself. You can manipulate it. You can do whatever you want with it. I don't care. I just want you to have fun, and because this is really fun. Okay, so that is what we're going to do in the next video.